All right, we have a couple more theorems to look at. The first one is for the limit of a composite function. So if you have the limit as x approaches c of f of g of x, then we would do direct substitution, making the limit as x approaches c of f of g of, now we're substituting c in for the x. That's our direct substitution. So that would be g of c. And then if we do the limit as x approaches c of f of g of c, if you look here, the limit as x approaches c of g of x is L. And so we would have f of, and then that limit, which is L. So there's the limit of a composite function. And then for your trig functions, it's just a matter of substituting in the c everywhere there's an x. So for sine of x, the limit as x approaches c for the sine of x would be the sine of c. The limit as x approaches c of the cosine of x would be the cosine of c. Limit as x approaches c of tangent of x would be the tangent of c. And this just goes on from there. So in each case, you are substituting in c where the x is. So your trig functions are easy to substitute into. I do want you to know your trig functions. I want you to know the basic four. So 0, pi over 2, pi, and 3 pi over 2. I want you to know all the trig functions of those basic four angles, as well as the angles that are in between. So at pi over 6, at pi over 4, at pi over 3, and so on around the circle, knowing those basic trig functions for all of those angles. We'll do an example later on in this video to hopefully jog your memory of what I'm talking about. So we'll take a look at some examples. I would recommend that on the examples, you might pause the video, work the example yourself, and then check to see if you did it correctly. So this first one, the limit as x approaches 4 of g of x, where you're given g of x is this rational expression. So that means we're going to substitute in a 4 everywhere there's an x. So that would be 12 times the square root of 4 minus 3. And then in your denominator, again, putting in a 4, and so having 4 minus 9. And then simplifying, that would be 12. The square root of 4 is 2. And in your denominator, you could go ahead and simplify 4 minus 9 to get negative 5. And then your last step, doing your final simplifying. So 2 minus 3 is negative 1 times your 12. You get negative 12 over negative 5, and that will then simplify to positive 12 fifths. For the part B of this one, the limit as x approaches 0 of g of x, again, the same g of x, so we're going to substitute in 0 everywhere there's an x. So 12 times the square root of 0 minus 3 over 0 minus 3. 0 square root is 0, so that'll be 0 minus 3. And then in your denominator, whoops, I put 0 minus 3, but I meant minus 9. Let me fix that. And then 0 minus 9, which is negative 9 in your denominator. And so negative 36 divided by negative 9 is going to give you 4 for the limit there. So again, that direct substitution. I'm going to erase these and scroll on up to our last two examples. So for the polynomial, we'll substitute in -3 everywhere there's an x, giving us 2 times -3 squared plus 4 times -3 plus 1. -3 squared would be 9, so 2 times 9, and then 4 times -3, giving us -12, plus 1. 18 minus 12 plus 1 would end up giving us a value of 7. And that would be good work that you could show for a polynomial like that. And your next one, number 3, is the limit as x approaches 7 of the secant of pi x over 6. So we'll start off doing direct substitution. That would equal the secant of 7 pi. I'm going to rewrite that, putting the pi behind the 7. So 7 pi over 6. I want to do one reminder for you. Secant is the same as 1 over cosine. So 1 over the cosine of 7 pi over 6. And so now we might take a look at your unit circle, just as a quick reminder. Pay no attention to the fact that the circle doesn't really look like a circle. So you have your corner angles, as I might refer to them, at 0, at pi over 2, at pi, and 3 pi over 2. And then as we look at where these get split up, here in the first quadrant, you have an angle pi over 6, and then you have an angle of pi over 4, and then you have an angle of pi over 3. I'm going to rewrite that pi over 4 a little bit better. And so in this problem, we want to be at 7 pi over 6. So one way that I like to count it out is if your denominators are either a 3 or a 6, then think of them in terms of a denominator of 6, and you can just count it out. So you have 1 pi over 6, and then pi over 3 would be 2 pi over 6. Here's 3 pi over 6, that would be pi over 2. 4 pi over 6, 5 pi over 6, 6 pi over 6 would be pi, and here is 7 pi over 6. So this is the angle that this problem is referring to, and you're doing cosine. So want to remind you that these angles are associated with ordered pairs, and so we have to think about what ordered pair would be happening at 7 pi over 6. Well, first of all, it's in the third quadrant, so we know that both the x and the y are negative. And then we just have to remember, so you have to think about your x, and your x is coming out across here a little bit longer. You are going to have to know that it involves either the square root of 3 over 2 or 1/2, and then you got to figure out which one's which. And at 7 pi over 6, the square root 3 over 2 is the x, and the 1/2 is the y, with both of them being negative. So now, as we go back to where we were in the problem, we had 1 over the cosine of 7 pi over 6. So that would be the same as 1 over. All right, cosine is x. So your cosine is x and your sine is y. So that would be the same as 1 over the x value there, the negative square root of 3 over 2. And then that will simplify doing the reciprocal to negative 2 over the square root of 3. And then we can rationalize that denominator. So multiplying by square root 3. And your final answer is negative 2 square root 3 over 3. Now, something that happens quite a bit in calculus is that you have to do sometimes quite a bit of either manipulation or algebra, and you kind of lose sight of what you were looking for. So always go back and look to see what is it we were trying to find. Well, we were trying to find a limit. And so maybe you make a final statement for yourself that L equals, and then what it was that we found. I think that is always helpful to look back, see what it was that you were trying to find.